welcome into lecture number 7 of Calculus 3. This lecture is going to be about partial derivatives. So let's start this lecture with some geometric motivation. And what we're going to do is consider ourselves, suppose that we have a function of two variables. So geometric motivation. So let's let f be a function of two variables. And really, let's actually regard the output of f as a z value and consider the graph of this function. And let's suppose, for the sake of this argument right here, this motivation, that the graph of the function is really nice and really smooth. And so maybe the graph of the function just looks like some nice smooth surface in space here. And so I'll draw the x, y, z coordinate axes in three-dimensional space. And so remember how this works. We're going to regard, if we regard this as the graph of f, gamma f here means the graph of f, then the idea is that for every point in the domain, let's say this point right here is a point in the domain, maybe its x and y coordinates are a and b, then this point right here is just a point in the domain, right? But the output of the function assigns a height to this point. And so maybe the height is right here, and this height is going to be z. And this z is going to be equal to f of ab. So that's the output of the function, right? And so for every point in the domain, the function assigns a height, and so the graph looks like a surface like this. And what we want to do in this lecture is talk about how can we measure the rate of change of this surface, of the graph of this function, this surface, as this point moves in the plane down below. And we're going to restrict ourselves to only two types of movement down below. So the first thing we're going to do is, let's suppose that we fix this point b. So let's suppose that we fix y equal to b, and we just consider the portion of this surface that sits directly above the line y equals b. So if we do that, y equals b is going to look like a line in the xy plane, right? So this is our line y equals b. And once we fix that, then actually in the three-dimensional space, this line is going to actually become, right? It's going to become a plane. So this plane right here that I've drawn, this blue plane, is now the plane y equals b. And the idea is that this plane will now slice our surface. It'll slice the graph of the function, okay? And we can then think about the trace of our curve in that plane. So this lighter blue curve that I've just drawn is supposed to be, or we're imagining, that this curve right here is the intersection of our graph of the surface with the plane y equals b. So we have fixed y equals b. We're letting x vary still, so x is still allowed to vary. We're still letting the z direction vary, and our surface has become a curve in some sense, right? So we're now able to restrict our study to this curve of intersection of the surface, gamma of f, the graph of f, and the other surface, y equals b, which is a plane. All right, and at this point, we can talk about this curve as though we were studying Calculus 1, right? So this curve, if it's smooth enough, which we'll define later on as we move forward in this chapter, but this curve, if it's smooth enough, will have a tangent line at this point, right? So at this point, it will have a tangent line. And so we can sketch that tangent line here, and then you can probably guess what we really want to do is find the slope of this tangent line, right? So I'm going to call this tangent line t sub x. So even though this lives in the plane y equals b, the variable that's changing at this point is the x variable. This plane is parallel to the x-axis, or the xz plane, I should say, right? So this plane y equals b is parallel to the xz plane. So the change in the slope basically is going to be with respect to x and z. All right, and so we're going to define then. Again, this is like our motivational setup, but we can define the slope of the line, so the tangent line t sub x. So I named it t sub x, right? That is tangent to the surface, and the surface is our graph again, right? To the surface gamma of f at the point a, b, f of ab, and this line lives in the plane, or lies in the plane y equals b. So we have fixed the y coordinate, and we're just looking at the other two slots changing, right? So that So in other words, if I highlight this, the y value is fixed, right? And the only changes, the changes are coming from this, right? AF of A, so nearby that. So we're going to use that to write a definition in a minute, but first, like a formal definition with a formula. But right now, this kind of heuristic definition is going to state, so what are we going to call this? We're going to call this slope. So the slope of this tangent line, that's a derivative, right? Slope of a tangent line is an instantaneous rate of change, and therefore it's a derivative. And this, because there's, you can already probably imagine we're going to do the same thing in the other direction, right? So because there's more than one, we're going to call this the partial derivative with respect to x. So this slope is what we're defining. So this is called, so define this, well, I've written this in a kind of weird way. Let me regroup here. So define the slope of the tangent line t sub x that is tangent. So now I'm defining the tangent line, right? So t sub x that is tangent to the surface gamma f at this point and lies in this plane. Define this to be the partial derivative of f with respect to x. So this is important at this point, right? And this is at the point AB. All right, so there's some motivation for the partial derivative with respect to x. Now, I alluded to this just a minute ago, but how could we extend this idea, or change this idea to be the partial derivative with respect to y, to the other coordinate in the domain, right? So partial derivatives are always going to be with respect to the variables that come from the domain of our function. And so the idea is exactly analogous, but just a little bit different. And so for this one, we'll fix, if we fix x equal to a, right, then we get a line in the domain plane, in the xy plane. We get a surface or a plane, right, a plane in the xyz coordinate space that is parallel to the yz plane. And then it cuts our surface, just as this one did. It's going to cut our surface, and maybe it cuts it like this, right? Something like that. And so the tangent line to this point that lives in this plane, this one will be t sub y, and its slope, right? So this tangent line is t sub y. This lives in the plane x equals a. And this one, the slope of this line is the partial derivative with respect to y, the y partial derivative of our function. Okay, so the geometric interpretation here is very important. These two tangent lines now kind of, by the way, meet each other. They're living in entirely different planes. So they meet each other at this point and nowhere else, right? The green one is living in the plane that's parallel to your screen, but it's out at this value of x equals a, but otherwise it's parallel to your screen. And the blue plane here is like coming directly out of your screen, orthogonal to your screen. It's parallel to the xz plane, and it's at this fixed value of y. All right, so now that we have this kind of geometric idea of what these are, let's write down some definitions and actually talk about how to compute these things. So, and then some notation. There's lots of different notation, it turns out, for partial derivatives, but we'll get to that in a moment here. The first thing we want to know is how can we compute these things, right? And so let's go back to the one that we've written out, in detail here, the heuristic definition of. We want to take the limit somehow, right, of a derivative. So a derivative is always a limit of a difference quotient. So I'm looking at the blue, the dark blue tangent line here, t sub x. So what did we do? We fixed the y equal to b, and then if we're going to define this by a limit, we're going to look at tiny changes, right, tiny changes in the x direction. So we're going to look at tiny changes here. So like maybe x plus a plus ah and a minus h in this direction. And then obviously as that changes, you'll get little secant lines, and we know what a derivative is, right? But the idea is that the limit will only work in the x direction because we've already fixed the y value in this case, right? So here's our limit definition of the x partial derivative. I'll write this down. So these are our limit definitions of partial derivatives. And I think you'll see that these are exactly what you expect them to be, just we need to be a little careful how we write it, right? So let's let f be a function defined on an open set. So this means, again, there's room around the point, right? An open set containing our point AB. So containing our point AB. Then the partial derivative of f with respect to x at this point AB is the number. So it's the number given by the following. So the most basic notation that we're going to use for this, and then we'll work from here with all the other notations. So but the defining notation is going to be this curly d by curly dx. So df by dx, but the d is curled here. It's kind of a curly d. And this indicates that this is a partial derivative and not just a regular ordinary derivative. And this is going to be taken, so this is going to be evaluated at our point AB, right? And so in our x direction, this is going to be defined to be the limit as h approaches 0 of f of a plus h comma b, so tiny change in the x coordinate, minus f of ab, all divided by h. And this is exactly a difference quotient, just as we talked about up here, right? So let me color code this exactly the same way. The b's remain fixed, right? The b's remain fixed. We've fixed the b, and what makes this a partial derivative in the x direction is that we have this tiny change in the x coordinate, right? Tiny change in the x coordinate. So this is the definition, but we have to add one more line. Anytime we define something by a derivative, we have to always say that this is the number, right, provided the limit exists. So there's no guarantee that this limit will exist. Depends on the function, right? But provided the limit exists. All right, and so then we can probably guess how the y partial derivative is going to be defined, right? So I'll just write this one here as similarly, and you can fill in the details for the rest of this, but similarly, df by dy at this point, AB, is going to be equal to the limit as h approaches 0. This time, we're going to change the roles of the a and the b, right? The x and the y coordinates. So this time, our x coordinate is going to be fixed, and our b coordinate is going to be varied a little bit, right? That's our y coordinate, our value b here. And so then we're going to subtract off f of ab and divide by h. And so it's very similar, right? But this change happens in the y component only. That's why it's the partial derivative with respect to y. All right, so these are our limit definitions of partial derivatives. And you will notice that these are exactly the limit definitions of derivative, right, in the respective coordinate or component, right, only. So we fix one component, and then we take the derivative with respect to the other one. Okay, so there's the idea. Let's write that down, and then we'll talk about notation, and then we'll do some examples here. But the idea is the following. So when taking a partial derivative with respect to one variable, you can only do one variable at a time, even if you have a function of more than one variable, right? More than two variables, I mean. You still can only do one variable at a time. So with respect to one variable, you consider all other variables to be constant, and you take the usual derivative. So we have fixed those, right? We fixed the b on this one, we fixed the a on this one. And this is the idea. So, and at this point we take the, what I'll call ordinary derivative, with respect to the one that we wanted to take the partial derivative with respect to, right? So in our mind, like as a mental exercise, you just consider all other variables to be fixed and constant, and then you take the derivative with respect to the one variable that you're concerned with. All right, so again, before we talk about examples, let's talk about notation, because there are lots of different ways to write down the notation or denote a partial derivative. This one right here is the most common and probably the best. Unfortunately, it also takes the most writing, so therefore that's why there's other. It's one of the reasons why there's other notations, because people get lazy. They don't want to write this out. So here are some options for ways to write this. So here's our partial derivative with respect to x. This can be written, by the way, you can write in your arguments here. So you could write this as a function if you want, like this, or you can write it as a function. So this one is evaluated at a point. This is the function as a function of x and y. Or if it's just implied that it's a function, you can just leave it like this, right? So that's not really too much of a leap right there. It's just different ways that you can write down a function evaluated at a point as a function with its arguments, or just as the function itself. All right, but then the different notations for this derivative itself are the following. So the one that our text uses the most and likes the most is my least favorite and the most dangerous. And that is just to write a subscript here. So f sub x. This is dangerous because later in the semester, this is going to mean something different to us. So and then at that point, it's going to mean two things, and we have to be very careful about which thing does it mean, right? So I'm rarely going to write this in the lectures, but you will see this in the text and in the homework a lot. So you need to know what this means. This means the partial derivative with respect to this function, of this function with respect to x, right? Now, to kind of maybe take care of this, but still not have to write this whole fraction, but to use the same idea, we'll also see like a capital D sub x of f like this. So now this says the x derivative is operating on f somehow. And then my favorite is to kind of mix these two and to write this as curly D sub x of f like this. And this is common as you move forward. And it's becoming more common among math people. To write the partial derivative symbol with a sub x here, that just means d by dx of f. All right. So that's one way. Now, of course, you can take multiple partial derivatives, right? So you can take, say, two partial derivatives of f with respect to x, and you can write it like this. So what does this mean? Well, this means the partial derivative with respect to x of the partial derivative of f with respect to x. And so this means exactly the same thing as what you would see in calculus 1 or 2 with a regular d here, an ordinary d. This is just the partial derivative version. The question then becomes what happens if you mix these, right? Because now we have more than one variable. So it is legal to do something like this. And if you write this, the order matters. What does this mean? It goes from left to right. So really what this is saying is that this is it goes from closest to the function out is what I should say. When you read this, though, the way that this one is written, you can just kind of write it the way it was written. You have to be careful. So actually what's happening here is that the y derivative is acting on f first. You take the y derivative first, partial derivative, and then after that's done and you get a new function, then you take the x partial derivative of this new function, right? So in general, this is not the same then as taking the x derivative first and then taking the y derivative. So this one would be d squared f dy dx downstairs, but again, the dx derivative operates first in this scenario, right? Now, this is not in general the same, but we will talk about this again soon. Now, we need to make sure that as far as we're concerned right now, these two things are different, right? Order matters, and these are different. And we'll talk about criteria when these might be the same or when they will be the same a little bit later on in this lecture. Okay, what we really need to be careful of here is how are we going to use, say, this notation or even this notation in this for these multiple derivatives. So here's one, f sub xy like this. Everything always, so this is the rule of thumb, okay? You always work from the function, start closest to the function and work away. So always start closest to the function. And then work out. Work your way out, away from the function. So in this case, this is going to be the x partial derivative first, then take the y partial derivative, right? So in other words, this is the y partial of the x partial. Well, which one is that? Well, let's just follow the notation, right? So this is going to be df by dx sub y. This is just different notation for the same thing. But then this is going to be, of course, the y partial derivative of the x partial derivative. And look what happens here when we kind of translate between these two different notations. Here we have x and then y, right? And here on this side, we still have x and then y, but notice that they've changed, right? The order has changed because of the way that these two different notations work. So closest to the function, work your way out. So x has to be first over here, right? Because it's closest to the function here. And of course, I forgot to write the f up here. That's got to be there. All right, so these are all the different notations for derivative. Just be careful, though. Be careful. Same thing with this one. This is actually, these two are going to behave more like this, all right, because they're on the left. They're working from the left to the right. This one, this little subscript, though, works from the right back to the left. So the subscripts are always going to be backwards from the other notations here. All right, so that was a lot of discussion about notation, but it's important because you're going to see all these different notations as we work forward in this semester, and some of them are confusing. Especially this one is the easiest to like type, and therefore the textbook uses it frequently when maybe they shouldn't. But it's good. We just have to be used to it. We have to again remember how it differs, especially how it differs, but how it's the same and how it differs from the other notations for derivative. All right, now that we've gone through that whole spiel, let's do an example. So what I would like to do now is consider the following function. Let's say we have this function of two variables. F of xy is equal to 2x squared y squared minus 3xy. And for this one example, I would like to use the limit definition. Use the limit definition. All right, actually use the limit definition to compute these two partial derivatives, df dx, at some generic point a, b. Now, the domain of this function is all real numbers. This is a polynomial, right? So all points in the plane, I should say, all points in R2. And again, it's a polynomial. So we would guess that if functions of multiple variables behave like functions of single variables, then this derivative should make sense at every point, right? And it does. But let's compute formulas for both of these derivatives, df dx and df dy, at some generic point a, b. So take a moment to work this one out yourself. Use the limit definition. So use the limit definition, and then we'll make some observations when you guys come back. All right, let's work this one out and see how it goes. Remember what we want to do, if we're going to take the x partial derivative, so if we want to take the x partial derivative, then what we need are f of a plus h comma b and f of a comma b. So let's just write this out. This one is 2 times a plus h squared times b squared minus 3 times a times b. And then we should work this out, right? So this one's going to be 2b squared, I'm going to leave that there, times a squared plus 2ah plus h squared, of course, right? Minus 3ab. And then we also need just f of ab, just regular f of ab. And this one's going to be 2a squared b squared plus, minus. I made a mistake up here, right? This a should be a plus h. A plus h. B, a, so this can be, I'll write this one out in two different terms. So this one's going to be 3ab minus 3hb. Okay, and then what do we have here? This one's just going to be, if it's just ab, then this one's going to be 2a squared b squared minus 3ab. And then we need to subtract these, right? So f of a plus h comma b minus f of ab. This is going to be all of this. So I'm going to write this one out as 2a squared b squared plus 2b squared times 2ah plus h squared minus 3ab minus 3hb, and then minus all this, right? Minus 2a squared b squared minus 3ab. And then we see 2a squared b squared minus 2a squared b squared and negative 3ab minus 3ab. Those are all going to cancel, right? So those are all going to cancel. And what we're left with then is this 2b squared times 2ah plus h squared minus 3hb. And we can factor an h out of all of this. So you're probably having flashbacks to Calc 1 now, right? So you can factor an h out of all of this. And what we're left with then are, and we can multiply this through now, so 4ab squared plus 2hb squared minus 3b. Right, that's all that's left after multiplying through. We have our h. And now we're ready to take our limit, right? So our partial derivative with respect to x at ab is going to be the limit. As h approaches 0 of, let's write out the formula, f of a plus h comma b minus f of ab all over h. And then this is the formula on top, right? So this is the limit. As h approaches 0 of h 4ab squared plus 2hb squared minus 3b all over h. Of course, those h's cancel in a limit. And what's going to be left here? 4ab squared plus 0. There's an h here, right? So that one's gone. So minus 3b. And that's it. So there's our partial derivative with respect to x. So df dx at ab is just equal to 4ab squared minus 3b. All right. Now that you've seen this, I'm going to let you guys work out the y derivative if you haven't already done so. The y derivative is literally exactly the same because this is a very symmetric function. The x's and the y's will just change roles, so it's not exactly the same. But they're going to change roles. It's going to be pretty much the same, though. Very analogous. So you can work through exactly the same way. What I would like to do, though, before we move forward, is make an observation here. That really what we could have done, and we observed this earlier, actually. I said up here, right here, right? Idea. When taking a partial derivative with respect to one variable, you consider all the others to be constant and take the ordinary derivative. So we did the limit definition here, and we got this answer, right? Let's try to do it as the idea up there suggested, which is to just take the x derivative of this while treating the y's like constants. So let's rewrite our function. Remember, our function was f of xy equals 2x squared y squared minus 3xy. And then take the x derivative of this function. So this is what we're going to do here is treat the y's like constants, right? So the derivative of 2x squared y squared is going to be 2y squared times the derivative of this x squared, because the 2y squared all behaves like a constant. Derivative of x squared is 2x, right? Minus, same thing here. The 3 and the y are all constants with respect to x, and the derivative of x is just 1, right? And so, as a function, this is going to be, we can rearrange it now, right? But this will be 4xy squared minus 3y. And then we can plug in our AB, our point AB, after taking the general derivative here. So df by dx at this point AB is going to be 4ab squared minus 3b, and then we compare. It's the same, right? It's the same. And so that means that actually we don't have to use the limit definition in cases where we can actually compute the derivative like this, using our rules from Calc 1. All right, so that's good news. That means that sometimes you should never ever forget about the limit definition. It's important conceptually for sure. And we will talk about the limit. We'll return to the idea of the limit definition frequently as we work through this course and this semester. But to actually compute in a scenario like this where you can take the derivative without using the limit definition, then you can just do it, right? You can do it just as you were doing it in Calc 1. Okay, so this whole idea, everything we've done so far has been with functions of 2 variables. So 3 variables total. We have the 2 domain variables and then the 1 range or codomain variable, which was the z component where the surface lived, right? The graph of the surface lived. But this extends in a very straightforward way to functions of more than 1 variable. So I'll write it this way. This idea extends straightforwardly to functions of more than two variables. All right, the difference is that once you get into 3, 4, 5 variables in your domain, you can no longer envision, you don't have this geometric picture, right? So even if you have three variables in your domain, you can then not slice, right? You can't slice through your domain with a plane anymore, your surface with a plane. You have to slice through with a three-dimensional, you know, analogy or analogous thing to a plane that's three-dimensional, which we can't imagine, right? Because we only live in three-dimensional space. So, and that's the way most of us think, in three-dimensional space. So the two-dimensional version is very good for the motivation, the picture. You can see the slices here. You can draw the picture. It's all good, right? 3 dimensions, you have to imagine that you're doing that without being able to actually see it and draw it. But the idea is exactly the same. And so what we can do then is just the same idea, right? We can just compute these derivatives. So if we have a function like w equals e to the xy times the natural log of z, then we can compute all the partial derivatives here. So we can compute dw dx, dw dy, and dw dz, just as we described above. So consider all the the variables that are not the one for which you're taking the partial derivative. Consider those as constants and just compute the other derivatives. So I'll give you guys a minute to compute these derivatives, and then we'll check back in. All right, let's see how you did. Again, when you take these derivatives, so dw by dx, you're going to treat all the other variables as constants, right? So this is going to be, I'll just write it out in a few steps here, but d by dx of e to the xy natural log of z. All right. In this scenario, the y and the z are constants. So number one, this log of z is a constant. That can just come out. The y is wrapped up in the function, so there's going to have to be a chain rule here. But the chain rule is going to say, okay, the derivative of e to the xy with respect to x is itself, e to the xy, times the derivative of xy with respect to x. The derivative of xy with respect to x is just y, because y is just a constant here, right? So this is just times y. And so then we could rewrite this in kind of more in the order it was given as y e to the xy times log of z. All right, or you could leave it this way. It doesn't matter. As long as you have parentheses here and, the log is only being applied to z, then you're good. All right, the derivative of w with respect to y is going to be very similar because, again, symmetry, right? This function is symmetric with respect to x and y. If you switch them, nothing changes, right? The derivative is the same. But let's write it out. So this is e to the xy times log of z. We're taking its derivative with respect to y. So derivative of e to the xy is this time going to be e to the xy times the derivative of xy with respect to y. So times x, right? And then times log of z, which is still a constant. That's a constant with respect to x and a constant with respect to y. All right, so very similar, a little bit different, but very similar, right? All right. The last one is the derivative of w with respect to z. This time, so I'll write it out again, but this time e to the xy, that entire term is going to be a constant because neither x nor y are z, right? So neither of them depend on z. So this e to the xy just hangs out. It's carried through. It's a constant. And the derivative of log of z is 1 over z, right? And so there we go. That's the derivative of w with respect to z. It's e to the xy over z, or 1 over z times e to the xy. So that's how that works. Very straightforward, right? You just one by one go through the different variables. You treat all the other variables like constants, and everything works out just like it would in Calc 1 or maybe Calc 2. I mean, derivatives are Calc 1, right? So it works out just like Calc 1, except it has some other variables there that you've treated like constants for the time being. Okay, let's talk again about higher order partial derivatives. So we talked about it only up here when we wrote out the formulas, right? The notation up here. We talked about how the order matters in these things, but let's actually investigate this highlighted not equal sign here. So I claim that in general, we can't just assume that these are equal. So let's first investigate a function that we can compute the second partial derivatives of. So let's consider this function, f of xy equal to, let's say, sine of x plus y plus e to the xy squared. And what I would like to do for this one is I would like to compute and compare. So compute and compare the two mixed second partial derivatives. So that's going to be d squared f dx dy. So this one, remember, means y first, then x. And this one, d squared f dy dx, this one means x first and then y, right? As far as the partial derivatives go. So let's compute these and see what happens. So for either of these, we have to start with the first derivatives, right? So we need to take really 4 derivatives to compute these two. So we need our first partial derivatives. Let's start with df by dx. That's going to be the x partial of this whole thing, right? So let's just write it out now. Derivative of sine is cosine, right? So this is going to be cosine of x plus y. Chain rule applied to the inside. Derivative of x plus y with respect to x. It's just 1, right? So that's just cosine of x plus y. Plus derivative of e to the xy squared. So e, that's itself, e to the xy squared times, chain rule, derivative of the upstairs with respect to x. So that's going to be a y squared down below, right? All right, let's do the same first derivative, but with respect to y now. The first term is going to be the same, right? Derivative of sine is cosine. So this is cosine of x plus y times the derivative of x plus y with respect to y. It's 0 plus 1. It's just 1, right? Plus the second term, again, starts off the same idea. Derivative of e to the xy squared is e to the xy squared times the derivative of the upstairs of x times y squared with respect to y this time. So this time it's 2xy that comes down, right? So derivative of derivative of e to the xy squared with respect to y is 2xy e to the xy squared. All right, so far they're different. The two first derivatives are different. Now we want to take the next thing we want to do is take the y partial derivative of the x partial derivative and then the converse of that, or the inverse of that, right? The x partial derivative of the y partial derivative. So we're going to take d by dy of df dx. So now we're taking the y derivative of this stuff, right? All right, let's see how it goes. The y derivative of cosine of x plus y. That's going to be minus sine of x plus y. And then again, chain rule says the inner derivative is 1, so that's it. That's all we get, right? So that's done. Now we have to take the y derivative of this term. Well, that's going to be a product rule, right? Because we have a y squared times e to the something with y in it, right? So as a product rule, this will be derivative of the first, so that's 2y, times the second, e to the xy squared, plus the first, y squared, times the derivative of the second with respect to y. Well, we just computed over here, that's 2xy e to the xy squared, right? So 2xy e to the xy squared. And then we can kind of simplify all this. So this is going to be minus sine of x plus y plus 2y e to the xy squared plus 2xy cubed e to the xy squared. That's upstairs. E to the xy squared, right? All right, we can leave it like that. So that's nice and organized. So that one's done, right? So let's take, I'll draw a line right here. Let's take now the x derivative of the y, df dy over here. See what happens. All right, first term, same deal. Derivative of cosine is negative sine, and the chain rule is going to say the inner derivative is 1. So this is minus sine of x plus y. And same deal. Now the x derivative of the second term is going to be a product rule because we have x down below and an x upstairs multiplied together. So this is a product rule. So derivative of the first with respect to x is 2y leave the second alone, plus leave the first alone, 2xy, times the derivative with respect to x of this term. So that was y squared e to the xy squared. We computed that earlier, right? And then, just as we did before, combine anything that needs to be combined, and we notice, look what happens. This derivative is going to be minus sine of x plus y plus 2y e to the xy squared plus 2xy cubed e to the xy squared. All right, and now we compare. We've done the compute, now we compare. Sine of x plus y on both of them, right? 2y e to the xy squared, both of them. And then 2xy cubed e to the xy squared, both of them. So these are exactly the same. So for this example, these do equal each other, right? For this example, or for this function, we can say. And these are equal to each other for all points in the domain, which is actually the entire real plane, right? These functions are both defined and differentiable, continuous, etc. on the entire real plane. So for this function, we can say without any doubt, right, that d squared f dy dx is equal to d squared f dx dy. But like I said, we cannot just assume that this is true in general, and this is not a proof that it always works. This is only proof that it works for this function, right? But it does, though, make us think, this function is not, there shouldn't be anything super special about this function. There might be, but there shouldn't be. So this makes us think that maybe this idea is more general than what I've stated here, right? And it is. It turns out that it is. There's a theorem for that. So whenever there's a general idea, that's a theorem. And this is actually a very important theorem. So this is a very important theorem. Note. Mark this down. Whatever you have to do to make sure that you know this theorem, right? This one's very important. This is called Clairaut's theorem. And we will use this throughout the semester. We'll talk about this all the time. All right, so you have to know when I say Clairaut's theorem, you have to know exactly what I'm talking about. So here's what Clairaut's theorem says. Suppose that f here is a function of two variables. So suppose f is defined on an open set D. Remember, open set means that it doesn't contain the boundary elements, right? So open set D that does contain our point AB. So containing the point A comma B. All right. If the functions, and now I'm going to use the book's bad notation, all right? So f sub xy and f sub yx. These are the same exact partial derivatives that I wrote up here, and they're in the same order, right? xy means x first, then y. Yx means y first, then x, right? So if these functions are continuous on this open set D, so these functions that are built by taking two partial derivatives, if they're continuous on this open set D, then a couple things are true. So these derivatives that we wrote down before, these are equal, oops. So it's exactly these functions, right? But the idea is that these functions are equal on the entire set D. So not just at the point, but in a neighborhood. We call this a neighborhood, in an open set containing the point, right? So it's not, if they're equal at the point, that's not enough. They have to be equal at the point, and they have to be continuous on an open set, right? And the continuous will take care of the rest. But if they're continuous on an open set that contains the point that we're worried about, then those partial derivative formulas will be equal on the entire set D. So like I said, this is a very important theorem. We're not going to prove this theorem. I will let you believe this one. But the idea is exactly what we've illustrated from this example, right? So these second partial derivatives are definitely continuous. They're actually differentiable. They're really nice functions, right? And they turned out to be equal. It will always work out that they're equal. So what does this mean, right? So what? Well, there's lots of important meanings from that we'll draw from this theorem. But one thing then that this means that when this theorem applies, right? So when Clairaut applies, or Clairaut's theorem applies, there are only 3 second partial derivatives to compute instead of 4. And that sounds like not a big deal, but it reduces the amount of work you have to do. All right. So instead of 4. So the partial derivatives that need to be computed then are like d squared f dx squared, that's x twice, d squared f dy squared, that's y twice, and then d squared f dx dy equals, so either one of these, right, you only have to compute dx dy or dy dx. So these just get combined into one thing. You just have to compute one of them. And depending on the function, one order might be much easier than the other order, right? Okay, this whole idea extends to even higher derivatives. So this theorem, I should say, this extends to higher order derivatives as well. So under the same conditions, meaning that the whatever the partial derivatives you want to be equal are, they must be continuous on that open set, right? So whatever they are, in that case they would be third, fourth, fifth, whatever, sixth derivatives, right? They have to be continuous on the set D, then they're equal to each other. So under the same conditions, we get things like d cubed f dx dy dx is the same as d cubed f dy dx squared, right, is the same as d cubed f dx squared dy, whatever, right? So in other words, you can choose the different orders of x, 2 x's and 1 y. These are the 3 different possibilities, right? Either y first, y second, or y third in this case. In that case, it reduces the number of partial derivatives you have to do by even more, right? So all 3 of these are equal, therefore they collapse into one computation if you're sure that Clairaut applies, right? So this is a time-saving theorem for us, a very important theorem for other reasons, but also because it's going to save us time. All right, let's end this lecture with one more example. So frequently, you guys might see in your for other studies, for your other classes, you might see people talk about partial differential equations. So a partial differential equation is an equation that relates the partial derivatives of an unknown function, and then you have to solve for that function. All right, let's just look at one example, and this is a very famous example here. So, and we'll see other examples as we move forward, but we're not going to do too much with partial differential equations, but like I said, you will see these in your other classes as you move forward in your education. But one really important example here of a partial differential equation is Laplace's equation. And we'll see this again later in the semester, so it's a good one to look at now. Laplace's equation can be done in any dimension, so let's just write in 2 dimensions. So in 2 dimensions, Laplace's equation says the following. The second derivative of, we'll call it u, it's usually called u for whatever reason, u for unknown maybe, but du dx squared, d squared u dx squared. So the second derivative of u with respect to x twice, plus the second derivative of u with respect to y twice is equal to 0. That's Laplace's equation in 2 dimensions. All right? In 3 dimensions, you can probably guess what's going to happen. It's going to be the same d squared u dx squared plus d squared u dy squared plus d squared u dz squared equals 0. All right? So these are called partial differential equations. These are Laplace's equation. So you will see, and again, like I said, we'll talk about this later in the semester as well, but there's a symbol for this. So in either case, if you draw a triangle of u like this, this means d squared u, let's just do the 2-dimensional version. So here, let me write it this way so that it looks like you can see how it works. d squared squared by dx squared plus d squared by dy squared of u. And so this just means, okay, apply these derivatives to u and then add them up. So this is called the Laplacian of u, and Laplace's equation says this Laplacian equals 0. All right, we're not going to talk about how we would actually solve this equation if we were just given this equation, not in this course. When you take a course on PDE, or partial differential equations, you can talk about how to solve this. But what we need to be able to do in this course is verify that a given function is a solution of this differential equation. So what I would like us to do to end this lecture is to verify that this function u of xy equals e to the x sine of y. Verify that this is not the only one, by the way, but this is one of the solutions. So verify that this solves this Laplace of u equals 0 in 2D. So the two-dimensional Laplace's equation, which is this, right? It's this one. So what do you have to do? Take your two partial derivatives, add them up, and they should equal 0. So take a moment and work that out. Hopefully you get, when you take your partials, you add them up. Hopefully you get 0. If not, come back and we'll finish that one off together. So let's take a look at this one. We need to take the second partial derivatives, right? So let's take the u by dx first. The x partial derivative, this is e to the x times, again, we treat sine of y like a constant, right? So this is just going to be itself. And if the first x partial derivative is itself, guess what? The second one is 2, right? So the second x partial derivative is, again, itself. So let's take the y partial derivatives. Might be more interesting here, right? But du by dy. Well, the derivative of sine is cosine, and e to the x is a constant with respect to y. So this is going to be e to the x cosine of y. And then we take one more partial of this, right, with respect to y. So this would be the second y partial derivative. Again, e to the x is a constant. The derivative of cosine is minus sine of y. All right? And then we're supposed to add these up, right? So d squared u by dx squared plus d squared u by dy squared equals e to the x sine of y plus negative e to the x sine of y. And of course, that's going to be 0. That's exactly what we expected, right? So that's just an example of how to verify that a function is a solution of a differential equation, in this case, Laplace's equation. And we're going to leave this lecture here. I'll talk to you guys in the next one.